Hi, we're presenting the multi-arm bandit problem and discussion of an information-theoretic analysis of Thompson sampling. Before we jump right into the paper, let me introduce you to what is the multi-arm bandit problem. Let's start with an everyday example. Suppose there's a new restaurant and a ramen bar near your apartment, and you are wondering which restaurant to go. In this case, you are actually experiencing an exploration-exploitation dilemma, where exploration means you are trying something new, trying something unknown, which can give you nice result or terrible outcome. For exploitation, it's like a safe option, which means you will go to the ramen bar you're familiar with and there won't be much surprise. And you're always taking the optimal action based on your current knowledge. Similar scenario happens in many situations, like ranging from choosing restaurant to spending $1 million in a research project. This multi-arm bandit problem is really common. So now we're going to see how we mathematically formulate this problem. So there's a finite action space representing the action you can take, and the outcome space. And you, as an agent, is going to make a sequence of action and receive a sequence of outcome. And then there is a P star, which is the true distribution or the joint distribution between action and outcome. And you don't actually know about it. And we have a reward function R, which evaluates the outcome. The larger the reward is, the better the outcome is. So we define the optimal action as the action that can maximize the expected reward, and regret as the sum of reward you can get from the model minus the actual reward you get from the model. And then Callan will talk about Thompson sampling, a method to solve the multi-arm bandit problem.
Thompson sampling is an algorithm for selecting actions that will ideally help us minimize our eventual cumulative regret. So, one distinction we need to make here is that Thompson sampling is a Bayesian approach. We are modeling the outcomes for every single action as a random variable. In this figure right here, we might have each of these three distributions corresponding to the outcomes of each of our three actions. And how do we choose actions? Well, we will sample the action that maximizes our expected reward. The paper we will be discussing is an information-theoretic analysis of Thompson sampling by Russo and Van Roy. Now, we need to make an assumption first, which is that we're using linear bandits. This means that actions are d-dimensional, and the expected reward of an outcome sampled from this action is going to equal the inner product of our action vector and some theta p. And eventually, we will show that the cumulative regret within t time steps is bounded by this function of the entropy of A star. And since the entropy of A star is actually upper bounded by the log of the size of the action space, this is quite a good bound because we can have a much better bound than these previous works. Here's a quick visual of the previous works for your reference. And now let's get into the heart of the proof. We will be defining this information ratio, which is, at a given time step, the difference or the ratio between the regret within that time step squared over the information gain for the optimal action. And what this is saying is that even if we're incurring a lot of regret, if we can bound the information ratio, then that means we're actually learning a lot about the optimal action, which is what we want. And proposition 1 tells us that if we can bound this information ratio, then we can express the expression right here, which is that the expected regret is less than or equal to the square root of gamma bar entropy of A star times t. And notice that if we replace gamma bar here with something that looks like maybe d/2, then we can show the result. So the first step in showing this proposition number 1, we will just do some algebra. We expand out the definition of regret, then we substitute in for the definition of gamma, and then afterwards we do some algebra, and we're left with this expression, this expected value on the bottom. And so long as we can bound this by the entropy of the optimal action A star, then we can prove the proposition and be on our way to solving the eventual problem. Ting Ting will present the rest of that.
So the next step is to find an upper bound for the expected summation of information gain. So to do this, for step 6, we use the definition of Z. And for step 7, we just use the extension of expected value. And for step 8, we use the chain rule of mutual information. And for step 9, we use entropy reduction form of the mutual information. And to get step 10, we can use the non-negativity of entropy value. And all these theories are provided in the appendix. So now we have an upper bound for the expected regress using gamma t. And now in proposition 2, we want to give an upper bound of gamma t. And notice that gamma t is the information ratio, which is the ratio of the expected difference of reward and the information gain. So in the first step, we want to have a bound for the expected difference of reward. So first, we have defined alpha and n, and then we can get the expression using claim 1. We find that it is exactly trace of n. And the next step, we want to find a lower bound for the information gain. To find this, for step 13, we use claim 2, and we can also use step 2 to find step 14, which is provided in the appendix. And for step 15, we use the Frobenius norm of matrix, which is further explained in the appendix. And now we have 2 bounds, and we combine them together to get a final bound for gamma t. And to conclude, we can combine proposition 1 and proposition 2 together to provide a final bound for the expected regress. Thanks for listening.